These are the notes on V.S.E.P.R, which is a little bit of an intimidating acronym in chemistry, but actually it's a fairly easy concept, and by the end of these notes you will have a basic understanding of it. We've begun to discuss molecules. So now you should be able to differentiate what is or is not a molecule. Remember that molecules are built out of covalent bonds only, no ionic bonds. So that gives them a particular shape, and that is what we're going to be exploring in these notes, the shapes of molecules and how they can be predicted. Remember that covalent bonds share a pair of electrons, or sometimes they share two pairs, a double bond, or sometimes they share three pairs, a triple bond, but they're always sharing a pair of electrons. That shared pair goes between the two nuclei of the atoms sharing them, and it creates sort of a shape, a structure to the molecule. Remember when we talked about electrons and how they're all very negative individuals and how they really find each other repulsive? Literally, they are repelled by each other. So we saw this within the atom, like there's the 1s orbital. And if they're repelled by each other, then why can that have two electrons in there? Oh yeah, that's right. They have two different spins, two different quantum states that allow them to sort of occupy the same volume. But within that volume, you can sort of think of them as staying as far as possible apart, AFAP. Within that energy level, or within that orbital in this case, they are sort of keeping their distance. And no other electron can get in there. Any other electron becomes excluded because there's no third spin. Once you've got the upspin and the downspin, every other electron is kept away from there. That is why electrons wind up in pairs. And those pairs of electrons sort of occupy the space, filling it up and excluding everything else. This is important because the same thing happens in a bond. A bond, remember, is a pair of electrons. Well, one of them must have an upspin and one of them must have a downspin. Once that bond is formed, it sort of protects that region, that volume, from other electrons getting in there. It sort of fills it up. Also, the fact that electrons find each other repulsive, it seems really simple, it seems really jokey, but this is what gives molecules their shape. This concept is really why molecules are shaped the way they are. So remember, they find each other repulsive, literally, but they can have two different spins, so they wind up in pairs. So if you have one pair of electrons over here, it's going to want to stay as far as it can from this other pair of electrons over there. As far as it can, but still trying to get near that nucleus. So that is what gives rise to the structure inside of an atom. And now you're going to see it gives rise to the molecules and the bonds between atoms. But the great thing about this is, when we're talking about molecules, we don't need to worry about all the electrons. We just need to worry about the important ones. What were the important ones again? The ones on the outside, what do we call those? Valence electrons. So when we're considering the shapes of molecules, we ignore the inner electrons, forget about those guys. Just the valence electrons matter. And they wind up in pairs, so they're pairs of valence electrons. That is how we wind up with the name of this concept, this theory. It is valence shell electron pair repulsion, which is a big mouthful. That's a lot to say. So most of the time we shorten it to V.S.E.P.R. Now if you look at the word V.S.E.P.R, it's V.S.E.P.R. So it looks like it should be pronounced something like V.S.E.P.R, but hard to say that. And so a lot of times when that's the case, we sort of like say it slightly differently. We say V.S.E.P.R, okay? As if it were spelled differently. V.S.E.P.R theory predicts many molecular shapes based on the idea that pairs of valence electrons surrounding an atom repel each other. That's it. So if you can figure out how many pairs you have and how they can get the farthest apart from each other, well, guess what? That is going to be the shape of a molecule most of the time. That is going to predict what the molecule looks like. The only difficulty is that this involves 3D geometry, not just on a flat surface usually, but it pops out into the third dimension. So that is what VSEPR stands for, valence shell electron pair repulsion. Well, you know what the valence shell is, that's the highest energy level. Electron pairs, well, you know what that is, and repulsion, pushing apart. So it's actually not such a hard concept when you break it down, it just sounds bad at first. So according to V.S.E.P.R theory, the shape of a molecule is determined by the valence electrons surrounding the central atom. Now, a lot of times there is a central atom in a molecule. Sometimes this can be hard to determine, but usually there's one in the middle and the other one surrounding it. It gets a little trickier when the molecule keeps on going, if it's a long, what we call a chain molecule. But for now, and for high school chemistry, we often focus on the smaller everyday molecules, which of course are the most abundant, the most common molecules. So electron pairs are all negative. There's never been an electron found that was positive about anything. Okay, if it's a positive electron, it's actually a positron. That's antimatter. So let's not go into that right now. Let's just say electrons are always negative. Therefore, the shared pairs that form different bonds repel each other and remain as far apart as possible. So we don't have to worry about what all those inner electrons are doing. They're balancing each other somehow. We can ignore that. That maybe makes the atom bigger. All we need to worry about is the ones on the outside, the valence electrons, and some of those are going to go into bonds and others are going to be already paired. So we just have to figure out which ones are in bonds and which ones are already paired and figure out how they would spread each other out. How would they spread each other out to be as far apart as possible from each other? So remember that before you get to an energy level, you got to fill the one below it. That's Aufbau. So just assume that those inner electrons, like I said, are balancing each other out somehow. We don't really need to worry about that. All we need to worry about is the ones in the highest energy level. And they do something weird. They do something called hybridization. That means mixing, sort of mixing in a strange way, blending. So the s orbital and the p orbital, they're different, but it turns out if you're on the outside in the valence shell, you can't really tell. They sort of hybridize when they form bonds. So what you wind up getting is hybridization, and so we don't really even need to separate the s and the p orbital as long as we're dealing with the valence shell. All we need to figure out is how many pairs of electrons we're going to wind up with. And remember, we're usually talking about an octet, right? So how many pairs would there be in an octet? Well, remember that in the case of fluorine, it actually already has 7 out of 8 valence electrons. It just needs that one more, right? And then it can get that from another fluorine. And then it can pretend it's a noble gas, not really, but it can pretend, and we count it as an octet. So think about that. Each of those fluorine atoms in that molecule, in that fluorine molecule, has 4 pairs. Well, it thinks it does if you count the bond for each one. So 4 pairs is what makes up an octet, right? Because every pair is 2. 8 divided by 2 is 4. So pretty much a lot of the time, as long as we're dealing with octets, which we usually are, we're going to be talking about 4 pairs of electrons. Now the geometry of a fluorine molecule is pretty easy, because think about it, there's only 2 nuclei, right? What kind of shapes can you get with 2 dots? The only shapes you can get is a straight line. We call that a linear form, okay? They're linear, like a peanut. All you can do between the 2 peanuts inside the shell is you can draw a straight line between them. There's no other geometry you can come up with. So a lot of these little peanut-shaped molecules, they're all linear. This brings us to our first V.S.E.P.R form. For all diatomic molecules, molecules that have 2 of the same atoms stuck together, and we find quite a lot of these, they all have that peanut shape. And we describe that as A2 linear, Why? Because A is just a generic atom, something, and we have two of the same thing. So we either have H2 or O2 or Cl2 or N2 or F2 like we saw in our previous example. Those are all called diatomic molecules. Di means two atoms, and it's two atoms of the same thing. Okay? So a lot of our gases are like that. Like you're breathing a lot of these right now. At least nitrogen and oxygen, that's most of what you're breathing. Put those together, and that's over 98% of what you're breathing right now. So you're breathing a whole bunch of these diatomic molecules, little peanut-shaped molecules with a very, very simple V.S.E.P.R form. So notice how easy that is. And it doesn't matter which kind of bond. Remember we talked about how some of these have single bonds and some of them have double bonds and triple bonds. Well, it doesn't change the shape, does it? Because you can't do much with two atoms. If you have two atoms stuck together, pretty much there's no other choice, A2 linear. So remember how we said that fluorine could form a single bond with another fluorine and make a diatomic molecule? Well, because chlorine is in the same family, it does likewise. So a single bond can take care of fluorine. And remember how oxygen was capable of making a double bond with another oxygen and making a diatomic molecule, right? And then nitrogen was capable of making a triple bond with another nitrogen, making a diatomic molecule. All of those were A2 linear. But what about the next one over to the left? What about carbon? Well, carbon is out of luck. We don't find carbon gas. I mean, carbon is in some gases, but we don't find gas that is pure carbon because that would have to be a diatomic molecule with two carbons stuck together, two carbon atoms, and that would need what kind of bond? A quadruple bond, which of course we don't see. So carbon needs to be more creative. If carbon is going to satisfy its octet, it needs to do a lot more work. And then we'll discuss the other ones further to the left later, but let's examine carbon now. Carbon is very far from having an octet. Carbon needs to do a lot of work to become stable. So if carbon goes looking for something to bond with, what is it most likely to come across? Well, the most abundant element in the universe, the most common element, is hydrogen, so it can grab a hydrogen and make a covalent bond. But unfortunately, that doesn't do it for carbon. We need to bring in more. Notice, you can see where this is going. Once we bring in two hydrogen, okay, it's not going to work either. We still got those unpaired electrons on the top and the bottom. Remember, whenever you see an unpaired electron, you know that is unstable. That can't work. So, bring in another one. And of course, we need just one more. And this is the molecule that we call CH4. So you might think it would be called carbon tetrahydride, but it's not. It is called methane. Methane is a very, very common chemical, and it exhibits a very particular shape. Now, looking at that, you might imagine, oh, those bonds should be 90 degrees apart. Looking at it on a flat piece of paper, that would make sense, because they are kind of evenly spread out. All of them are 90 degrees apart, so you might imagine that would work. Remember, each of those bonds is a pair of valence electrons, right? And those valence electron pairs repel each other, V.S.E.P.R. So if they got as far apart as possible, you might imagine 90 degrees would do it. But unfortunately, it doesn't, because you need to picture the third dimension here. But before we get to the actual shape of methane, oh, by the way, I should mention that methane is a gas that contains carbon. Okay, it's just not made of pure carbon. Let's talk about another gas that contains carbon, carbon dioxide. Okay, this is a simpler one. We'll do the easy ones, then we'll build up. So for carbon dioxide, this is another way that carbon can satisfy its octet. it can double bond to an oxygen and then double bond to another oxygen. Well, carbon only needs 4 bonds, so that takes care of it. Because of this geometry, carbon dioxide is actually linear. So notice, because there's only 2 other atoms that carbon is bonded to, and so that's 4 pairs of electrons that are being shared there, but they're in 2 different sets, the double bonds. Those get repelled to opposite sides, like if you spread out your arms in opposite directions on the 2 sides of your body, and that's where the oxygen would wind up. If you were the carbon, that's where the oxygen would wind up. And then, of course, that is also linear. That is called an AB2 linear molecule. That is another V.S.E.P.R form. Another easy geometry in V.S.E.P.R comes from one of our stranger atoms. That atom is boron. Now, boron sounds a little bit like the word boring, but it is far from that. Boron is very bizarre. It does things that no other atom does, and one of those is that it will make an electron deficient molecule. It will make a molecule that defies the rule of the octet. For some reason, boron doesn't seem to want 8 valence electrons. It only seems to want 6. So the reason for this is complex, but let's just say boron just is happy. Just give me 6, I'll be fine. Now, boron starts off with 3 valence electrons. I'm not showing that here. So, of course, it can make 3 bonds, in this case with 3 fluorine, making boron trifluoride. This is one of the weird molecules that boron will make. Now, no other atom will do this. So boron is unique on the periodic table. Because of its strange behavior, it has actually been disowned by its family, and very frequently we call its family the aluminum family instead of the boron family. Some people will still call it the boron family because boron is at the top, but boron is so weird it often gets sort of disowned. So if boron makes 3 bonds, well, that's 3 pairs. And the great thing about 3 pairs is there's a very easy way for them to spread out. It's just like you would think. Think of a circle, 360 degrees. Think of chopping that circle into 3 even slices. We don't usually do this with pizza, for example. We usually like to cut all the way across, but you can't do that in this case. And what you wind up with is 120 degree angles. 360 divided by 3, 120 degrees. So it turns out that is the spacing that we get between those bonds, between the boron and the different fluorine atoms. So that is boron trifluoride. It's a very, very easy to see molecule. It's what we call an AB3 trigonal planar. Why is it called that? Because a trigon is a triangle. That's another name for a triangle. And planar means it's on a surface, like flat, like on a flat piece of paper, right? Because this molecule lies flat. Many molecules don't. In fact, most molecules don't. They sort of pop out into the 3rd dimension. But this one is easy to see because it remains flat, and it's just exactly like what you would expect. 3 bonds, spread them out evenly, that's 120 degrees, and boom. And there's a few other molecules that boron makes that have this form, trigonal planar. But it's a very unusual form because pretty much only boron makes it in terms of molecules. We do see this form frequently in what we call polyatomic ions, but for now let's just restrict ourselves to molecules. Now we come to the big one. The one that is formed by, as we spoke of earlier, methane, CH4. This is an interesting shape because even though, look at the circle on the top, it does look like it should be 90 degrees, it just isn't. Because now we can take advantage of the 3rd dimension. It turns out staying flat on a sheet of paper is not the farthest apart those 4 pairs of electrons that make those bonds can be. If they pop out into the 3rd dimension, they can get farther apart. And we wind up with a shape called a tetrahedron. So the tetrahedron is shaped like a four-sided die. If you've ever played D&D, you might have seen a four-sided die, or I guess they're available in magic stores for some reason, I'm not sure why. But the four-sided die has that perfect shape. This is one of the most perfect shapes there is, I guess, other than the sphere itself, which is probably perfection, like the ball. Other than that shape, this is one of the next best shapes there is. Because every one of those sides of the four-sided die is an equilateral triangle. Every side is the same length, every angle is the same angle, and it has four of those sides total if you count the one on the bottom, okay? And so it's not shaped like a pyramid of Giza, like in Egypt, which actually has four sides that you can see and a square bottom. This has no squares at all. Every side, including the base, the bottom, is an equilateral triangle. It's really a perfect shape. And this is the shape that the methane molecule forms. Many molecules form this shape, or even if they don't form this shape exactly, they have this shape embedded in their structure. So this shape forms an AB4 tetrahedral molecule. We see these all the time, many of these. And this is the most important of the V.S.E.P.R forms that you need to learn, the AB4 tetrahedral. And this leads us to the shape of the methane molecule. It is kind of shaped like a four-sided die, if you consider the hydrogen as the corners of that four-sided die. That is the shape of a methane molecule. So what is the angle between the bonds? Well, it turns out it's not a nice and neat number. It's 109.5 degrees. Ooh, that doesn't sound good. That sounds gross. We like things like 90, 120, 180. Those sound great. Even 45 isn't too bad. But 109.5? That just doesn't sound right. That's because the angles we use are designed for flat geometry. They are based around 60, which really is the one in the equilateral triangle, which is on a flat surface. But now we're talking about three-dimensional geometry, and unfortunately, in three-dimensional geometry, the angles don't come out so pretty. So 109.5 is the angle between any two adjacent bonds in the tetrahedron, okay? And they're all kind of adjacent because of the geometry. So 109.5 degree angle doesn't sound good, but that is good. That's as far apart as four pairs of electrons can get from each other in three-dimensional space. So the tetrahedron is a very important shape, and you can think of most molecules as being based upon this template with a 109.5 degree angle. And that's as far apart as those four bonds can be, and it winds up being as far apart as those four hydrogen can be from each other as well, because the bonds are what are positioning them around the central carbon atom. So what about the regular old water molecule? The water molecule, if you had to pick one, would probably be the most important molecule in chemistry. I'm going to say that. It's also one of the most abundant molecules in the universe. Hydrogen, of course, wins, but then water. So when you hear all these reports that water is so hard to come by in the universe, that is not correct. Water is all over the universe anywhere we look, but it's really hard to find liquid water. That's the problem. So if we look at the Lewis structure for water in the upper right corner, notice that it has two bonds and it has other valence electrons around the central oxygen. So it has two shared pairs of electrons. Think about it. Isn't a bond a shared pair of electrons? And it has two unshared pairs of electrons. Well, those are the other pairs of valence electrons. But isn't that still an octet? Isn't that still four pairs? And didn't we just see that four pairs can be farthest apart when they have a tetrahedral form, like the four-sided die. So actually a water molecule is still kind of a tetrahedron. We don't call it that because you can't see the tetrahedron. Look at that water molecule, okay, right above the die there. I'll replace it with the one that I make, okay. Look at that shape there. That doesn't look like a tetrahedron, far from it. But it's kind of like a tetrahedron where you're not seeing two of the corners. It's kind of like a plucked tetrahedron because those valence electrons aren't really visible from the outside. They're around the central oxygen, but they are still repelling the ones that are in the bonds. Not only are they repelling the ones in the bonds, they're actually repelling them more than the bonds are repelling each other, which winds up changing the angle slightly, okay? It's not the same as the 109.5 degrees that we saw in the tetrahedron. It's actually 104.5 degrees now. It squeezes those bonds a little bit closer together. You can think of it because the valence electron pairs have a greater repulsive effect because they're closer in to the oxygen. So they push apart a little more, squeezing those bonds just 5 degrees closer than they would be in a real tetrahedron. So again, a water molecule still is based on the tetrahedral template. It's just slightly modified. You've clipped off two of them. You can't see them from the outside. You can only see the ones that are making the bonds. And the angle is just a little different. I mean, 5 degrees is not a huge difference if you look from the outside from a distance. And we call this, the V.S.E.P.R form, is AB2. And then we need to mention those electron pairs. So that's E2, that's 2 electron pairs. And it's just described as bent. Sometimes we would give the angle as well, like 104.5 degrees, but we don't need to be that technical. We'll just call it an AB2, E2 bent. That's the V.S.E.P.R form. So now we're getting a little tricky with our V.S.E.P.R forms, aren't we? They started out easy, like A2, that was easy. But now we're getting a little more complicated. You could think of these three molecules as sort of transitional, one between the other, going from the tetrahedron at the top down to the bent water molecule at the bottom. This really helps you understand V.S.E.P.R form. If you understand this concept, then I think you've got it. Let's just say that. So notice at the top, all across the row, we've got CH4, that's methane. And it has that 109.5 degree angle, okay? That is what we call tetrahedral. That's an AB4 tetrahedral, shaped like a tetrahedron, okay? But then the next one down, NH3, doesn't exactly look like a tetrahedron, but it is a tetrahedron. It's just that one of those corners is no longer visible from the outside, because notice nitrogen has an unshared pair of valence electrons. Just like we saw in the water molecule, those act as the fourth pair. So there are still 4 pairs of valence electrons around the central atom. And of course, they push each other as far apart as they can. But again, like we saw in the water molecule, that pair is closer in to the nitrogen. It has a greater repulsive effect. And so it winds up squeezing those bonds a little bit closer than they would have been in a tetrahedron, down to 107 degrees. And then, again, we already said how a water molecule is also a tetrahedron, but it's been clipped even more so because there's 2 pairs that make up 2 of those corners that you can't see from the outside because all you can see are the ones that make up the bonds. So you can think of all 3 of these as just being modified tetrahedrons. The one at the top is the true AB4 tetrahedral form. The next one down is an AB3E because it does have a pair of valence electrons. That's what the E stands for. Pyramidal. We sometimes call it trigonal pyramidal, but I guess pyramids are triangular no matter what, so let's just call it pyramidal, okay? And the bottom one, as we already said, is the water molecule. That's the AB2E2 bent. So if you can see how these are related, if you can see how it's transitional from the one at the top to the one at the bottom, you just can't see all of the pairs in the water molecule or in the ammonia. The one in the middle is ammonia, NH3. You can't see all the pairs in those. It's still based on the tetrahedron. If you can see that, that's the fundamental idea that you're supposed to understand from learning V.S.E.P.R forms. Now, what's the byproduct of this? There's a major byproduct of V.S.E.P.R form. One thing is that it can affect the polarity. We already learned how to calculate whether a bond is polar or nonpolar, but let's say our bonds are polar. Let's just take it for granted. All of the bonds seen here in these images are actually polar. But in the case of carbon dioxide, because the polar bonds are pointed in exactly the opposite direction, notice how those red ones on the outside, those would both be the oxygen. Oxygen is the more electronegative element in this case. So the delta negative for the oxygen on the left would be on the left. The delta negative for the oxygen on the right would be on the right. So those are exactly opposite each other. And it turns out because of that, they will cancel each other out completely. You could also say the delta positives would cancel out as well. The delta positives, delta negatives for those particular bonds would be exactly opposite each other. So if you wind up with that linear form, okay, like we find in carbon dioxide winds up being a nonpolar molecule. Even though every single bond that's in carbon dioxide is a polar bond, because of that linear form, the bonds completely cancel each other out. The polarity of the bonds, excuse me, completely cancels out. But because the water molecule is bent, because it's based on the tetrahedral form, they do not cancel out. Because notice they are not exactly opposite each other. Water has very polar bonds as well, but they don't cancel. So you wind up with a delta negative on the sort of oxygen end of the molecule, and a delta positive, think of it as the bottom there, the hydrogen side of the molecule. The delta positive is sort of all along that side. So because of this, water has polarity. Very strong polarity, actually, because it comes from two polar bonds. And this is why water acts the way it does. This is why water can remain liquid at relatively high temperatures. That's because of that polar bond. This is why water likes to break apart ionic compounds. It's because of that polar nature to the molecule. Okay, so again, I shouldn't have said it's just the bond. It's the whole molecule that is polar. So it makes a big difference if you're a linear form, like the AB2 that we see for carbon dioxide, or if you're the AB2E2, like we see for the water molecule, which is bent. It makes all the difference, night and day. Couldn't be more different. So here we can see a bunch of the V.S.E.P.R forms. Now notice there was the A2 that was linear. I didn't mention the AB, but that is also has to be linear. Think about it. It's only got 2 points. All you can make is a straight line. We did not mention that one. We saw the AB2, like carbon dioxide, and then we saw the AB3, like boron trifluoride. We did not mention the A2B2, look down on the bottom. Okay, that's another form that we find in hydrogen peroxide. We did not mention the A2B2, but that's something we will see later in organic chemistry. And then we did look at the AB4, the tetrahedral form. We looked at the AB3E and the AB2E2, and those are really the main ones I want you to understand from this. We won't be getting into other weird forms like the AB6. We won't be getting into those. There are a few others that are exceptional to the tetrahedron, exceptional to the octet as well. But the only one of those I wanted to get into was the boron trifluoride. So if you understand what I was talking about, then you can sort of see, oh, I get it. I can see now why a methane molecule has that shape. I can see now why an ammonia molecule, that's the NH3, has that shape, or why the water molecule has that shape, or the carbon dioxide molecule has that shape. That is the point of V.S.E.P.R form. It's predicting the shape of the molecule from the valence electrons and the Lewis structures. So that is the end of the notes on V.S.E.P.R. And hopefully now you have a little bit of a greater understanding about why some molecules have that shape. I would emphasize the molecule water because it is so critical for everything, life on Earth, etc. So I would emphasize understanding the structure of the water molecule based on the V.S.E.P.R. theory.